Hello, can someone hear me? Perfect. Oh, right. So the notes are kind of the structure of the notes is really unfortunate because so today we're going to wrap up week 9, and I did not feel like making another set of notes for week 10 and then awkwardly going from complex numbers and complex vector space to the new topic. So I decided that I've extended the notes from last week. If my iPad was sharing the screen, then I could show you. So you should be seeing, so the notes updated, I think, when did I push it to GitHub? I think yesterday. So on my GitHub, there's already the new version of notes. And I'll upload those, I'll upload those as well on Quarkus later today. And then tomorrow we'll start fresh with the new set of slides for week 10. So I thought this was the, this would be the best to organize lectures. I realized only after starting this kind of weekly notes thing that it would be much more convenient to have it topic wise, and then it will be independent of when we finish a topic or not, and when we start a new topic. But that's late. No, I'm not planning a review for tomorrow because we're late and we short on time for the current content. So there will not be a review. If you want a review, I can basically do a review for everyone who wants one in my office hours. So if you ask me the right questions, it will technically be a review. But I don't have time tomorrow in the lecture for a review. One thing that I did want to remind you of before we go on, I realized that so in this 4.2 section, there's a proposition that we skipped in our lecture last week. I just wanted to remind you. So I'm just going to make this a comment before this lecture. Oh, no. Let me trash this. And then before. Okay, so just remark in section 4.2. We skipped proposition 4.24. Four point 2.4. But this follows as a corollary from the theorem that we did at the end. So if you look back at the end, from theorem 4.2.7. And what it says, so I just want to make you aware that we skipped this, but technically it's in the book. So so if you want to look at it, it says that well, this is not true. Sorry, I thought it was a different theorem, a different proposition. But just as what I can say is this can be used to conclude Actually, no, I think if I just say we skip this this proposition, then I don't want to spend time on this right now. So just make sure that you read proposition 424, and if you look at this, I would highly recommend you to have a look at this. And the main important theorem is 4.2.7, and that's the important bit. Okay, so last 15 minutes on last week Thursday, we ended up with did I cover? Okay, now I'm getting really confused. Let me just have a look. Oh yes, we did not skip this. Sorry, then this remark is even wrong. Okay. So Rosalind said exactly that we did cover this. No, I did at least state 4.2.6, but I skipped the proof. That's what I skipped. Oh, okay. So what I was referring to now I know what I wanted to say. Sorry, wasting valuable time. So the remark was supposed to be, I might as well just edit this out from the final video. In section 4.2, we skipped corollary 4.2.8 of the main theorem, which was 4.2.7. And it says that, I mean, look in the book for the exact, maybe more detailed version, but it says that if t goes from v to v, so this is a linear transformation with n dim v n distinct eigenvalues, is always diagonalizable, because, and the proof or the sketch of a proof, it's as in the book, it's was this proposition that we covered, that the dimension of each eigenspace e lambda I is exactly bounded by 1 on the lower side and m lambda I on the upper side, the algebraic multiplicity. So sometimes, just to warn you, sometimes people just say multiplicity without specifying algebraic or geometric, and then they mean algebraic. Because this is 1, then we know that theorem 4.2.7 is satisfied. Okay, but this is just really something I wanted to remark briefly, and now it's taking more time than I was planning to. Let's get back to complex numbers. I've introduced them to you last time, and we've kind of started to see how they work. They have a real part and an imaginary part, and there's a multiplication. So it's basically R2 is a vector space, but there's a multiplication, and this multiplication is similar to the multiplication of real numbers in the real line. And it has the interesting property that there's now a number which squares to -1, and this is something we haven't had before. So this is the most useful thing that we discovered in this new field of numbers. We're going to talk about fields today. So now let's discuss, let's talk about this discussion. I'll give you 2 minutes to think about this, and then we'll see whether when we think about C as a real vector space, whether this is a real transformation or not, a linear transformation. Okay, any ideas? So in the chat, there was just a question whether how we can view C as a real vector space. And remember that C is just R2. So you could think of AB as this complex number A plus IB. You can think of this equivalently as AB as a vector in R2. So who has an idea whether one is true or not? Is it a linear transformation of real vector spaces? So how could we write, I mean, it just suggested on the right-hand side that we could write W in C as C plus ID. And then T, sorry, no, this would be Z. And then TW of Z is W times Z. But if you want to think about this as two tuples, we would have to write this as AB times CD, where this AB is fixed. So this is a fixed complex number, and only CD is the input, the argument. It's like multiplying a number by another fixed number, then that's would be a function from R to R. So if you write what this is, namely this is AC minus BD and AD plus BC, then we can see that this is indeed This can be written as a matrix multiplying the vector CD, and the matrix is A minus B, A plus B. So just B. No, sorry, I'm wrong. B and A. Yeah, this is correct. So just by knowing that A and B are fixed numbers, they don't change with the input. So they're independent of the input Z. I can create this matrix. So this is basically, this is the matrix representing multiplication with A plus IB from C to C. Well, and now the question whether when is this invertible? Does anyone have an idea? It's not a trick question. It's a very, yes, exactly. Yeah, determinant has to be non-zero. So this means TW, i.e. the matrix of TW, is invertible if and only if the determinant is non-zero of A minus B, B and A. What is this determinant? Well, this determinant is A squared plus B squared. And the interesting thing now is, well, so A squared plus B squared is exactly the length. So this is the norm. This is the absolute value of the complex number A plus IB. Well, the way you can see this is if you write this in the complex plane C, then this is A and this is B. So the length of this complex number, remember this was the imaginary bit, the one with the I, and this was the real axis. So this is the axis in R2 that tracks the real part of the complex number. Then the length that is the total length of the complex number. This is just the, how do you pronounce it in English? Pythagoras. The law of squares that well, it's technically the absolute value squared of the complex number. So this would be the square root of B squared of A squared plus B squared. So this means if someone tells you, well, compute the length of the absolute value of I plus IB, then this is A squared plus B squared. If it was a real number, then you would just take the absolute value and square it. Because if you compare this to the real numbers, so this is the complex world and this is the real world. Here you literally just have R. So there's no plane, there's just one axis. And then any A or say any minus A, the absolute value of minus A squared is literally just minus A squared. But here you have two components. You have a real and an imaginary part. So the absolute value is A squared plus B squared, and then the square root. And here, yeah, if you would actually say that the square root, the absolute value is the square root of minus A squared. Okay, so this means to answer the second question, yeah, I'll shrink this later. So this means that TW is invertible if the norm or the absolute value of W, which is a squared plus b squared, which is exactly the determinant of this matrix, is non-zero. But like which is the vector, which vectors, which complex numbers have absolute value non-zero? Every vector, every complex number that isn't zero. So this is equivalent with omega, W is not zero in C. So as long as A or B are positive or negative, non-zero, then this determinant is non-zero. Okay, any questions? This is just to get you used to complex numbers. Oh, and then maybe another question. Oh no, this is not the right time because we haven't talked about complex vector spaces yet. So let me just explain this discussion to buy some time. So and you can look at this later again. So now let's thinking about a transformation which takes a vector that might be written as a plus ib. So this is b, and this is the length a, and it maps it to a minus b. What does that do? Well, the a part is unchanged, but now we have minus the imaginary part, meaning that the new vector is literally just mirrored across the real axis. So this is the real axis, this is the imaginary axis. And well, the answer to the first one is yes, we can think about this as TF of AB is going to A minus B. And then this means that the matrix of this is just 1 and minus 1. So that's the matrix representing it. The eigenvalues of this, as you can see, I mean, this is diagonal. This is a diagonal form. So the eigenvalues are +1 and -1. And the eigenspace of the +1 of the +1 eigenvalue is equal to a plus ib, such that b is equal to 0, meaning that this is the real. This is really bad notation. This is use notation R. So this is the real line inside the complex plane. So when you think about this whole thing as it's pretty bad. If you think about this whole plane is C, you can think of just this line as being the real line embedded into this. And the eigenspace, I mean, it's clear that if you have a vector which is completely inside the real line, so it's a vector with just an a and no ib, and you just perform this transformation, well, then it's just a. That's why I can say that there's a plus a eigenvalue, and the eigenspace is exactly all the numbers which with 0 imaginary part. Well, can someone guess what the e minus 1 eigenspace is? Yes. It's a very concise answer, but that's correct. And I guess like writing in the chat is very cumbersome. So it just means that a has to be 0, so it has to be purely imaginary. And this is just notation. So you usually write the complex unit I and then R, but don't worry about the notation if this is confusing. So the last question, I don't really understand. Do you mean whether how I know that the eigenspaces of these are the real and the imaginary axes? So if you look at this, this transformation just mirrors a vector from here to here. It just flips the b part, the imaginary part, from positive to negative or negative to positive. So if a vector is completely in here, it will just not flip because it's on the mirror axis. You can also, yeah, that's correct, Matthew. You can just verify this with the matrix, but I was trying to give you some intuition. Of course, algebraically, this is also, you can just do this algebraically. And if you have a vector which has only an imaginary but no real part, then it just flipped to minus itself. So that's so you can see this. Well, and the nice thing that the third part, the third observation is, if you compose T with T on A plus IB, this is T of A minus IB, and then this is A plus IB again. So it is its own inverse. This means T inverse is equal to T. And this operation is usually called complex conjugation. So and usually we don't write T for this, but we just write A plus IB and then a bar over this. And this is A minus IB. I don't know if you're going to need this, but this is just notation. So instead of writing T of a complex number, we just write the complex number and then put a bar over it. So this would mean that would look like this. If this is Z, let me write this in a different way. If this is Z, then this would be Z bar. So taking the bar means mirror this across the line. Okay. Well, now we get to a more formal part, but don't be afraid of this formal part, because so we've realized that the complex numbers have this advantage of having a square root of -1. That's point one. The second point is, well, if you want to have do all the linear algebra things that we've done so far in this semester, we need to like construct everything that we've had so far, vector spaces, transformations, and such for more general numbers, not only real numbers. And this is the beginning. This is the starting point. So a field is just an abstract idea that generalizes, or that for which we have a prototype, which is the real numbers or the complex numbers now. So remember, imagine that all the properties that real numbers and complex numbers have abstractly will be called a field, and there are more things that behave similar to the real numbers and the complex numbers. I didn't want to type all this in LaTeX, so I'm just going to write this by hand, but that means I have to find, yeah, here we go. So field, as you've seen, the real numbers and the complex numbers, this might be confusing with a vector space, but this is like the step before vector space. So don't think about this as a vector space, because vector spaces don't have multiplication like we do here. Okay, so we have two operations, addition and multiplication, and you can just think of them prototypically as multiplying two real numbers, adding two real numbers, or as we see now with complex numbers. So then we have certain axioms that we want to have to satisfy. So the first one is that, which is commutativity, meaning that x plus y should be y plus x for all x and y in the field. So I could literally write C or R, but to make this abstract, we just call this F. Okay, and then we have, as a second point, we have associativity. And this means if I have 3 numbers in the field, then it doesn't matter in which order I bracket them if I sum them all together. So this is again for all x, y, and z in F. Third point, third axiom. There is a 0 element. So just like in a vector space, or the 0 real number, or the 0 complex number. So that if we add this to any vector, sorry, any real number, any number in the field, it doesn't change it. Next one is an inverse. So for all elements in the field, there's an inverse, so that if you add the inverse to the element, it's going to be 0. Okay, let me just continue. We have maybe I should just bracket this later. So again, commutativity, but this time for multiplication. So we know that x times y is equal to y times x. Associativity, x, y, z is x, y, z no matter how you bracket them. I'm gonna make a note that this is for multiplication, and what we've had above, this is all, because I don't want to write too much, this is for the addition. Okay, so then same for the identity. This is point. Oh, there's one more before. So there's the distributivity. And this actually concerns both. So this means that when you encounter a sum and then a multiplication, this is the sum and this is the same as 2 multiplications summed together. Now we get to number 8, which is the identity. So this means there is 1 in F such that 1 times x is equal to x for all x in F. So you can see how these repeat for addition and multiplication. And yes, so the question in chat, if this is different from a vector space, it's very different. Well, what does it mean? Very mean. There are things here that you don't have in a vector space. Maybe you can think about which ones you don't have in a vector space. Number 9 is that now this is interesting. So the inverse of an addition it has to exist for every single element in the field, but the inverse for multiplication only has to exist for non-zero elements. So we exclude 0 from this condition. And then we want that x and x inverse multiply to 1. And that's it. So first of all, vector spaces don't have multiplication to begin with. And the other difference is we didn't have scalar multiplication here. So that's also different because we didn't fix like we don't have like real numbers and that they multiply with scalars. So that's different. Okay, any questions? So now let's have a discussion. Which of these are fields? Where multiplication and addition is defined in the usual way, like the obvious way that you've probably been using since, I don't know, when you learn multiplication? Middle school, I suspect. Well, fields can be used for anything that you want to use a field for. So that's a question by Jency in the chat. They're basically the foundation for a vector space. So you usually build vector spaces over fields. And that's actually the next step of what we're going to do today. There's literally a zoo of different mathematical objects. So if you ever want to investigate this, just go to Wikipedia and type in, start with the 1, and then there'll be many links to many other structures. So on vector space multiplication, you don't have multiplication between two vectors in a vector space. It just doesn't exist. We never defined it. We never wanted anything like this. We only wanted to have scalar multiplication. So we have scalars. And I never mentioned scalars in the definition of a field. And the reason is they will be scalars for a vector space. No, we don't call them vectors. They're just called elements of a field, numbers. Okay, so who can tell me if these are fields or not? Yes, so Andrew said n is not. Can you also say why? Exactly. So 3 in n has no inverse for addition, simply because -3 is the thing that we would want, but this is not a natural number. They only start at 1. Okay, Adrian.
Yeah, I think the integers aren't either because they don't have the multiplicative inverse.
Yes, exactly. So if you define multiplication just in the usual way, we multiply two integers, then there's a problem because say 3 is in Z, but it has no inverse for multiplication, because 1/3 is not an integer. What about Q? So Q is indeed a field, and you can verify that you can multiply. You have P over Q with 7 fractions, and you can maybe have A over B, and you can define this to be PA over QB, and you can also define P over Q plus A over B to be, well, you'd have to have some common denominator, and then you would have PB plus QA. Okay, what about R? Yep. What about R plus? Only the positive, the non-negative. Yeah, this is not a field. And then again, additive inverse. And C is a field. Okay, so before time runs out, I want to give you one example of another field that usually we don't use that much. And this is the finite field with p elements, where p is a prime. So in this case, this means that fp, we usually start with 0, 1, 2, and so on, and then we go up to p minus 1. So it's the elements 0 to p minus 1. And if you want to have, if you say you have a and b in fp, then a plus b has to be, well, so addition is a plus b mod p, because a plus b might be greater than p minus 1, so it's not necessarily in the set fp. But in order to produce something in the set again, because remember, it has to be multiplication that has a value in the set of the addition, we just mod up by p. This means we divide a plus b by p, and whatever the remainder is going to be the result. And again, we take multiplication mod p. Okay, so let's look at this exercise. And if you have already ideas, let's just go at this, and we'll just answer this. So Shun's question is the first what you wrote. So this is a plus b mod p, because a plus p mod b mod p is not necessarily in fp. If say b is already in there, then it doesn't make a difference to mod up by p. So so basically f3 is this field with 0, 1, and 2. And I want you to write down this table for addition. We have 0, 1, and 2, 0, 1, and 2. And then the place here, there would be the sum of the column and the row. And the same for multiplication. Can someone just tell me what this is without any spare time to discuss or to think about it? I don't know what Yuan's question means. It doesn't show anything. So this example is just, I mean, what I could tell is that this is a field. AE, all axioms above. Hold. Well, I guess, yeah. So what about the inverses? This is interesting because we said that n is in the field because we don't have the additive inverses, but now we're gonna observe something. Okay, so what is 0 plus 0? That's 0. What about 1 plus 1? So 1 plus 1 mod 3 is equal to 2 mod 3, which is still 2, because mod 3 doesn't kick in if you're within the range of 0 and 3 minus 1. Now, what is 2 plus 2 mod 3? Yes, this is 4 mod 3. And the remainder, if you divide 4 by 3, is 1. So you always have to think about how many 3s can you stack into a tower that is of height 4, and what's the space that's kept empty. This means there's a 1. Okay. what about the other spaces? So 0 plus 1 is definitely 1 and 2. Same with this. What about 2 plus 1? Let's keep the addition on the left-hand side. Someone tell me what is 0 plus 1? Sorry, no, 2 plus 1. Mod 3. Yeah. This is 3 mod 3, and this is exactly a multiple of 3, so it's 0. And same here. Okay, so right-hand side. Can someone tell me? Okay, so there's a few cases which I guess we can just fill out, because 0 times another number is always 0. It doesn't matter if you mod out or not. What is 1 times 1 mod 3? Well, it's still 1. What about 2 times 1 mod 3? It's still 2. So the only interesting thing here is 2 times 2 mod 3, which is 4 mod 3, which is 1. Okay, so who can tell me something about the other questions here? Who can answer some of these questions based on these tables? Two mod 3 is 2 because well, modulo works the way that it's the best way to explain this. So if you have n and you have m, this is m. And the question is, how often does this fit in? And then this remaining space where m is too big to fit in here. But this is like, I guess I feel like this drawing is not helping. So modulo is if you divide, if you compute, say a mod p, what is this? So a mod p is a is a multiple. So this is m times p if it's a multiple, but maybe you can exactly, this is not true for all the a's, because if it's on a multiple of p, then you can't do this. But you can choose this, choose the largest m such that m times p, or the absolute value of m times p, is still less or equal than a. So if I have to take absolute values to like make it true for all the negative. Oh, I guess if you want to talk about, yeah, let's say a is a natural number. So a and n, sorry, p are an n. Then if you take the largest number such that m times p is less or equal than a. And then if we do that, that's step 1. The second step is we add r so that m times p plus r is a. That's the second step. So you can always find an m and an r such that this is true. And actually they're unique. So if you have a p and an a, you can always stack up as many p's as you can to just go under a. And then the remainder is R. So this is so this works for M and R are unique. And then A mod P is equal to R. Exactly, this rest. So if you look at this, if you want to compute 2 mod 3, well, what's the Q? How many times can you put 3 into 2? 0. So this means that, and 0 is allowed, it doesn't matter. So this is 0. And then what's the rest? How much? I mean, you have 0 so far. And then how much is there left over? What's the remainder? It's 2. So this is why 2 mod 3 is 2. How about 4 mod 3? Now this is a somewhat non-trivial example. This is maybe a bit more informative. How many times can you fit 3 into 4? Exactly 1 time. So this means this M will be 1. What's left? I mean, if you put another 3 in there, then we'd have 6, and that's bigger than 4. So this algorithm tells us to stop at 1. And now the rest, between 3 and 4, the thing that we couldn't fill up with p's is 1. So that's the one that we have to add, and then that's the remainder. So A mod P computes the remainder of the division of A by P, even if it's not possible to divide nicely. Okay, so let me go back to the chat and see. Yes, so Jency wrote so right. Should I write this? Yeah, let me just write this, the answers to these questions. So the commutative is clear because this is symmetric. So if you look at only the diagonal, it's like it's symmetric matrix. It's like if you transpose this table, which doesn't really make sense to transpose it, but what I mean is that these entries in this table are the same on both sides of the diagonal. So it is commutative. Because the table is symmetric. How can you conclude that 0 is the additive identity? Well, I think that's what Jency wrote. Let me just rephrase this. So because these two are the same, because the top column is the same as the first column in the table, this means that 0 doesn't change. Doesn't change the element when you add it to it. And the same is true here. These are the same columns, rows. So this means that that we can just I think do this in one step. What's this number 3? So this is 3 and 5. So 3 and then immediately 5. Equal to the top row 0, 0, 1, 2. And the same thing is true for the multiplicative. Identity. We can see that, well, let me just let you fill in the gaps. As I said, these rows are the same. And now we come to the inverses. So this is something like I want to mention before I end the lecture in like a minute or two. So this is important because so how do we see that there's an additive inverse is, yeah, this is number 4. Exist because every row contains a 0. So this means every row here has some 0, either it's here, here, or here. So this means this is the reason why there's additive identity. So why there are additive inverses. So the additive inverse of 1 is 2, for example. This is this means that 1 minus 1 in F3 is 2. Why? Well, if you have if you add 1 plus minus 1, well, what do you mean is 1 plus 2? This is MAT3. Oh boy. This is 0 because 1 plus 2. So you don't have to reach 0, but you just have to hit a multiple of the prime p. And then same is true for, I guess it's 0.6. So here in every column there is a 1, except for the 0th column as the 0th row. So this means because every row contains a 1. Except the 0 row. Multiplicative to all x, to all non-zero x in F3, which are literally just 1 and 2. And to test this, well, what is the inverse of 2 inverse? So 2 inverse is equal to 2, because 2 times 2 mod 3 is 1. And that's the condition. So an inverse is a number that multiplies with the original number to 1. Okay, so this is not quite as far as I was hoping to get, but there's only 3 pages. So we'll do this. We will start with this tomorrow in the beginning. And let me see if there are any questions. Let's see any questions about the context. Okay, so no, there will not be a review session tomorrow because we are behind the schedule. So the reason that the review session for the midterm, the first midterm, was because we were actually quite ahead of the schedule. Not ahead, but we were ahead of the other sections, and now it's the opposite. So no, we can't accommodate a review session. But let me end the lecture. So if there are no more questions, I'm just going to end the lecture. And if you have questions about a review, like if you want to review something particular, just stay for the office hours right now. And I'm happy to go over any past material. But I'll stop the, where do I do that? Let me stop the recording. You're free to go. This is the end of the lecture.